So this is 3.4, which is called a library of functions. So most of this section deals with a variety of function types that you need to recognize, that you need to know the parent function and the characteristics of it. So it would be important just to get this stuff in your memory, try and recognize these as best you can. The first one we're going to look at is the constant function, which is f of x equals b, or y equals b. It is a horizontal line, which goes like that. It has a domain of negative infinity to infinity. Its range is just the number b, as it only has one y value it goes through. It doesn't have any x-intercepts. Its y-intercept is 0, b, that point right there. It is an even function because it has y-axis symmetry. And for any number x, the y value is b. Our second function that we're looking at is the identity function, f of x equals x, or y equals x. This is a diagonal line here that has a slope of 1 and a y-intercept of 0. The domain is negative infinity to infinity, and the range is also negative infinity to infinity. The x-intercept and y-intercept are both 0, 0 here at the origin. It is an odd function because it does have origin symmetry. And here's a table of values of points. So when x is negative 2, y is negative 2. Negative 1, negative 1, 0, 0, 1, 1, and 2, 2. Our third parent function is the square function, f of x equals x squared. This gives us a parabola, which looks kind of like a U. The domain is negative infinity to infinity. The range is 0 to infinity, so it starts here at 0 and goes up to infinity. The x and y-intercept are both 0, 0, the origin. It is an even function because it has the y-axis symmetry. And here's some points for it. When x is negative 2, the y value is 4. Negative 1, 1, 0, 0, 1, 1, and 2, 4. Our fourth parent function is the cube function, f of x equals x cubed. It looks kind of like this. This is called a cubic. Okay? It goes down on one side and up on the other side. And it kind of twists as it goes through the origin there. It has a domain of negative infinity to infinity, a range of negative infinity to infinity. The x and y-intercept are both this point here at the origin, 0, 0. It is an odd function because it has origin symmetry, so reflect and then reflect. And then here's your table of values, negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, and 2, 8. All right. Our fifth one is the square root function, f of x equals the square root of x. Looks kind of like this. Notice it doesn't go before 0. Because if you try to take the square root of a negative number, remember that that gives you an imaginary. And we only talk about real numbers when we talk about graphing functions. Its domain is 0 to infinity with 0 included. Its range is also 0 to infinity with 0 included. It has a y-intercept and x-intercept there at the origin, 0, 0. It's neither, because it doesn't have y-axis symmetry and it doesn't have origin symmetry, so it's not even or odd, it's neither. And this is one of the ones that has different values here for your table. These x values, notice they are all perfect squares, so that way you can take the square root of them. So the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So this is one of the ones that's different, and it's just because you want the x's to be numbers that you can actually take the square root of. All right, number 6 is the cube root function. F of x equals the cube root of x. So it looks kind of like this. It has a domain of negative infinity to infinity, a range of negative infinity to infinity. The x and y-intercept are both there at the origin, 0, 0. It is an odd function because it does have origin symmetry. If you take a point and reflect and reflect again, it does match up over there. This one also has a different table of values because for these x's, you want them to be perfect cubes, so that way you can take the cube root of them. So the cube root of negative 8 is negative 2. The cube root of negative 1 is negative 1. The cube root of 0 is 0. The cube root of 1 is 1. And the cube root of 8 is 2.
Good morning, teachers.
Alright. Our seventh one is the reciprocal function, f of x equals 1 over x. This is called the reciprocal function because whatever number you plug in, it gives you the reciprocal of it. So if you plug in 1/2, you get the reciprocal, which is 2. If you plug in 1, you get the reciprocal, which is 1, etc., etc. The domain of this is negative infinity to 0, union 0 to infinity. It does not touch at 0, so there's no including there. The range is also negative infinity to 0, union 0 to infinity, because the y values here don't touch 0 either. It does not have any x or y intercepts, because it does not touch the x-axis and it does not touch the y-axis. It is an odd function, because you can reflect across this and then across this, and the points will line up. And then here's your table of values. If you take negative 2, the reciprocal is negative 1/2. If you take negative 1, the reciprocal is negative 1. If you take 0, the reciprocal of 0 is undefined, because you can't have it 1 over 0. You can't divide by 0, so it's undefined. If you take 1 and plug it in, the reciprocal of 1 is 1. And if you take 2 and plug it in, the reciprocal of 2 is 1/2. Right. Our eighth function is the absolute value function. F of x equals the absolute value of x. Looks kind of like a V here. Okay. Remember, absolute values take whatever you plug into them and make them positive. So like when you plug in negative 2, you're going to get a positive 2 as your answer. The domain on this one is negative infinity to infinity. The range is 0 to infinity with a 0 included. The x and y intercept are both 0, 0 at the origin. It is an even function because it does have y-axis symmetry. And then our table of values, negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. All right. Our ninth and final parent function is the greatest integer function. Now, different textbooks write this function differently. Some of them write them as f of x equals int of x. Some of them write it as f of x equals x with brackets on it. And some of them write it as f of x equals x with double brackets on it. Okay. It just depends on the textbook, which notation they use, but they all mean the same thing. They all mean greatest integer function. Now, the greatest integer function is a function that gives you the greatest integer without going over that number. It's kind of like The Price is Right a little bit. It's the biggest number without going over. Okay. What I mean by that is, if I plug in 1.5 into this function, the biggest integer, the biggest whole number that is not greater than 1.5 would be 1. If I did like 2.7, the greatest integer without being above 2.7 is going to be 2. And so the idea is that this function kind of rounds down. It always rounds it down to the next whole number. Okay? Now, for positives, that's pretty easy to do. So like 2.7, of course, that rounds down to 2. It gets a little trickier when you're over here in the negatives, though. If I say negative 2.5 and you want to round it down, it's not going to round down to negative 2 because negative 2 is to the right of negative 2.5. That would be rounding up. So when you round down for negative 2.5, you go to the left, which means you're going to go to negative 3. So negative numbers got to be a little more careful when you think about rounding down. Okay. This is a domain of negative infinity to infinity. We can plug any number in for x here. The range, though, it's just the set of integers. The y values are only at whole numbers. So negative 2, negative 1, 0, 1, 2, 3, 4, etc., etc. It's only the integers. All right. X-intercepts. This actually has an infinite number of x-intercepts. Every x in between 0 and 1 in this little line right here is an x-intercept. So any x's in that point, they are x-intercepts. It has a single y-intercept here at the origin at 0, 0. It is neither because it doesn't have y-axis symmetry or origin symmetry, so it can't be even or odd. And then this table is a little weird because the x's, instead of being precise points, they are intervals. So this says if the x is between -2 and -1, we round it down to -2. And that gives us this little segment. If the x's are between -1 and 0, we round it down to -1, which gives us this little segment. If the x's are between 0 and 1, we round down to 0, which gives us this little segment. If the x's are between 1 and 2, it rounds it down to 1, which gives us this little segment. And if the x's are between 2 and 3, it rounds it down to 2, which gives us this little segment. Okay. So it's kind of a different thing, but it's not too hard to do. You just always round down. Okay. All right. The next thing we're going to talk about is just a little bit of definitions. You'll learn a little bit more precise definition if you go on to calculus, but for right now, we're going to talk about continuous and discontinuous functions. And so for the sake of this class, a continuous function is any function that has no gaps or holes and that you can draw it without lifting your pencil from the paper. Okay. A discontinuous graph, on the other hand, is a graph that does have gaps or holes, and you have to pick up your pencil when drawing it. So 2 of these functions are discontinuous. This one right here, because to draw it, you'd have to draw this thing and then pick up your pencil and then draw this thing, pick up your pencil, draw this thing. So this is a discontinuous function. The other one that is discontinuous is the reciprocal function right here, because you'd have to draw this part and then pick up your pencil and draw this part. So these are the ones that would be discontinuous. Everything else you can draw without picking up your pencil. You can draw this one, you can come up here, you can draw this one. So the rest of them are all continuous. For the parent functions we've learned, only the reciprocal function and the greatest integer function are discontinuous. Okay? All right, so those are our parent functions. The next thing we're going to look at is piecewise functions. Okay? A piecewise function, or a piecewise defined function, is a function that behaves differently on different intervals within its domain. What that means is, for certain values of x, it might behave like a line. For other values of x, it might behave like a parabola. And for even other values of x, maybe it behaves like an absolute value. It just behaves differently on the different intervals. We call these different intervals pieces, so that's why this is a piecewise function. It has multiple pieces, and it's defined at certain intervals. And so our first example, the one that we're actually first going to do some math on, is a piecewise defined function. So example 1 here says the function f is defined as f of x equals this piecewise function, -2x plus 1, if x is between -3 and 1, with -3 included and 1 excluded. It behaves like 2 if x equals 1, and it behaves like x squared if x is greater than 1. And so the first thing it asks us to do is find f of -2, f of 1, and f of 2. Okay, so we're going to start with f of -2. We need to figure out which piece we can plug -2 into. Is -2 greater than 1? No. Is -2 equal to 1? No. Is -2 between -3 and 1? Yes. So I get to use this piece, which means I'll have -2 times -2 plus 1. -2 times -2 is positive 4, plus 1 gives us 5. Okay. The next one, we have f of 1. Okay. For 1, is 1 greater than 1? No. Is 1 equal to 1? Yes. So we use this function, and that function is just a number, and so there's no calculation involved. We just get 2. All right, and then the last one it asked us to find was f of 2. f of 2 is 2 greater than 1. Yeah, 2 is greater than 1, so we'll use this piece. So we'll have 2 squared. 2 squared is 4. Okay. So that's how you evaluate x values for this function. You just look for which piece you can plug into, and then you plug it in there. Part Part B asks us to determine the domain of f. Okay. Well, what's the smallest number we can plug in? Okay. If we look, this piece goes the smallest, and the smallest number it can plug in is -3. Can we include the -3? Because of the equal to, yeah, we can. Okay. Then we start moving forward. This piece goes from -3 all the way to 1, but it doesn't include 1. So you might think, okay, we have to stop at 1. But here's the thing. This piece has x equals 1, so we don't have to stop at 1. We can keep going. And so we keep going bigger than 1. Can we go bigger than 1? Yeah, x is greater than 1 here. So how big does this last piece go? Well, it goes for any number bigger than 1, so it can go all the way to infinity. This piecewise function has a domain that goes from -3 all the way to infinity. Part C asks us to locate any x-intercepts, any intercepts. We're going to start by finding x-intercepts, which remember that means y equals 0. So we're going to take each of these pieces and we're going to set them equal to 0. So we'll say 0 equals -2x plus 1, 0 equals 2, and 0 equals x squared. And we're going to solve them. For this one, I'm going to add the 2x over, so I'll have 2x equals 1. Then I'll divide both sides by 2, and I get x equals 1/2. Now, is 1/2 in the interval for this equation? Well, the interval for -2x plus 1 is -3 to 1. 1/2 is in that interval, so I can actually use that point. 1/2, 0. That would be an x-intercept. Our next equation, we have 0 equals 2. Is that a true statement? No. So that one tells us there's none for this second interval. And for our third interval, to get rid of the square, we would take a square root on both sides. And so we get x equals 0. Now before you box this in, you need to check, is x equals 0 in the interval for this piece, for x squared? If we look, x squared is for x's that are greater than 1. Is 0 greater than 1? No. So this one doesn't work either. You can make a note to yourself that it's not in the interval. Okay. You might even say interval for x squared. So it doesn't work. So we only have one x-intercept. We only get this one here at 1/2, 0. All right, and then we also want to look for y-intercepts, which remember that's where x equals 0. These are a little bit easier because all you got to do is figure out which piece you plug 0 into. Is 0 greater than 1? No, so I can't plug it in that one. Is 0 equal to 1? No, can't plug it into that one. Is 0 between -3 and 1? Yeah, so plug 0 into that one. -2 times 0 plus 1. -2 times 0 is 0. 0 plus 1 is 1. So we get a y-intercept of 0, 1. So those are a little bit easier to do than the x-intercepts. You don't have to worry about checking them because you already did the check when you determined which piece to plug into. So there we go. The next thing we're asked to do is to graph this function. Now, the first thing I'm going to do is I'm going to plot all the points I already know. So I have -2, 5. That's the point on my graph. I have 1, 2. That's the point on my graph. I have 2, 4. I have 1/2, 0. And I have 0, 1. So those are all my points. Now, right now, that doesn't look like much because it's not enough information yet. But at least we have those plotted. Okay. So what I'd like to do is I'd like to go and actually plot the rest of this. So I'm going to start with this first piece. This first piece goes from -3 to 1. So what I'd like to do is I'd like to know what I get when I plug each of these numbers into this equation. So we'll start with -3. If I plug -3 in, -2 times -3 is +6, plus 1 gives me 7. Now, do I include -3? Yeah, I do, because of the equal to, which means I can actually have a point there at -3, 7. I'm going to go here to -3, and I'm going to go up here to 7, and I'm going to plot a point. Then I'd like to know what happens at the other end if I plug in 1. -2 times 1 is -2. -2 plus 1 is -1. Here's the thing, can I include 1? No, there's no equal to here. So what that means is when I go to plot this point at 1, instead of doing a filled-in circle, I'm going to do an open circle, a hole, basically. So at 1, -1, I'm going to do a hole. So 1, -1, I'm going to put a hole right there. Okay. Now, what kind of graph is this function? Well, this function is a line. If we look at our points that we've drawn so far, -3, -2, 0, 1/2, and 1, can you see the line that goes through them? Hopefully so. So we'll take this and we'll just kind of connect and we'll draw a line, connect those together. And so there's the first piece of our graph. The second piece just says, if x is 1, the y value is 2. Well, that doesn't give us a line or anything. It just gives us a single point. It says, if x is 1, y is 2. So there should be the point 1, 2 on our graph. Do we have that point? 1, 2? We sure do. That point's already there. So we're okay. Alright. The last piece says if x is greater than 1, then we use x squared. Now if we look back at our parent functions, x squared is a parabola. It's the one that looks kind of like a U. So we should expect the graph to kind of look like that. We're going to start by plugging 1 into this thing, because that's where this number is. So if I take 1 and plug it in, what is 1 squared? 1 squared is 1. So I should have a point at 1, 1. But do I include 1 here? No, I don't, because there's no equal to. I can't include 1. So when I go to plot this point at 1, 1, I'm going to do another open circle, another hole. So I'm going to go to 1, 1, and I am going to plot a hole. There's that little hole right there at 1, 1. Then I'm going to pick some numbers that are bigger than 1 to plug in. We've already done 2 because we did it right here. When we plugged in 2, we got 4. Let's do another one. If we take 3 and plug it in, what is 3 squared? 3 squared is 9. So we could go onto this graph and we could plot 3, 9, which would be up here. And then we really aren't going to be able to go any further because if we did 4 squared, we would get 16, which would be way off the graph. So that's all we really have. So what we're going to do is we're going to connect the points that we do have together. So we have this point at 1, 1. We have this point at 2, 4. We have this point at 3, 9. And then we know it's going to continue going in that direction towards 4, 16, and 5, 25, and 6, 36, and all of those. And so we get kind of part of the U for the parabola there. Okay? So this graph, when we draw it, it has 3 parts. It has the line for this first piece. It has this point for the second piece. And then it has part of a parabola for the third piece. Part E asks us to use the graph to find the range of f. So remember, range is your y values from your lowest to your highest. Our lowest y value is down here at -1. Do we include that -1? Well, because this is a hole, we really can't include it, so we're going to have to put a parentheses on it. Okay? And then we start climbing up. And we climb up, and up, and up, and up, and then that arrow tells me it's going to keep going up, so it's going to go all the way up to infinity. There's our range. Alright, and then part F asks us, is the function f continuous on its domain? Well, can you draw this thing without picking up your pencil? Well, no, because once you get done with this line, you have to pick up your pencil to do this point, and then you have to pick up your pencil again to do this part of the parabola. So, no, it's not continuous on its domain. You're going to have to pick up your pencil to draw it, so it's not. Okay? Alright, our last example. This last example says, in the spring of 2014, Duke Energy Progress supplied electricity to residents in South Carolina for a monthly charge of $6.50 plus 9.971 cents per kilowatt hour for the first 800 kilowatt hours supplied in the month, and 8.971 cents for all usages over 800 kilowatt hours in the month. Part A asks, what would the charge be for using 300 kilowatt hours a month? Well, we know we're going to have this base charge of $6.50. And then we're going to have this charge of 9.971 cents. Okay. I'm writing it in terms of dollars rather than leaving it as 9.971 cents. Here it is as 9 cents, and then here's the 971 that goes after it. Now, I need to take that and multiply it by the number of kilowatt hours I had. I'm using 300 here, so I need to multiply this by 300. And then we'll go to our calculator and see what we get. So that gives me 36.413, which in money you usually round to 2 decimals, so this is 36.41. So it would cost you $36.41 if you used 300 kilowatt hours. Okay. Part B asks, what if you used 800 kilowatt hours? Okay. Well, we still have the $6.50. And we're using this one for the first 800 kilowatt hours. Well, we're still within 800, so we're still going to have the 0.09971. This time we're going to multiply it by 800. And so we get 86,268. And again, money, you would round that to 2 decimals, so this is $86.27 is how much you would get charged for 800 kilowatt hours. Now, before we get to C, I want to do one more question. I want to do, what if we had 900 kilowatt hours? Okay. Well, we already know we get charged this much, the 86,268 for the first 800. So I already have that much. Okay. But then after that, I get charged 8.971 cents for all the usages over 800. So I'm going to have that 8 cents and the 971 at the end. Okay. And then I have to multiply that by how much over I am. Well, how much is 900 over 800? Well, 900 is 100 more than 800, so I'm 100 over it. So I have to multiply that by 100. I'm typing in my calculator now. And so we would get 95.239 or $95.24. Now, notice we took what we had already paid for the 800, and then we just added into it how much we were over. We were 100 over. This is how much we get charged for each one we are over. That gives us our total. Now, I'm pointing that out because that will make Part C a little easier. So Part C asks us to write a piecewise defined function. So we're going to write a piecewise to represent the cost, C, for using X kilowatts per hour per month. So I'm going to have some function, C of X, the cost in terms of kilowatts per hour per month. Okay, and it's going to be a piecewise. So I'll draw my little curly brace there. Now, for this first part, it's actually pretty easy. we know we're going to have a base charge of $6.50, plus we're going to have this 9 cents and this little 9/7 of a cent times X, where X represents how many kilowatt hours we're going to do. And then we need to have if. We need to know when this happens. Well, this is going to happen from 0 kilowatt hours all the way until what? Well, this equation works for the first 800, so it's going to go all the way to 800. And then we're going to include both 0 and 800, because you're going to get charged this monthly amount whether you use 0 kilowatt hours or whether you use 800. And then 800 does get plugged in there. So that one's not too bad. It's pretty straightforward. It looks exactly like we did Part A and Part B. It's the second equation that's a little bit trickier. The second equation is for what if we're above 800? What if X is greater than 800? Well, that's where we kind of look at this other thing we wrote with the 900. We have to account for the first 800 that we already used, which means we need to pay this much money. We need to pay the 86.268, because that pays off the first 800. And then we need to pay for how much above 800 we are. So we're going to have plus 0.08971, but we don't want to multiply this by x, because if we multiply this by x, then I would be paying for this for the first 800 plus however much extra. Instead, what I need to do is I need to multiply this by x minus 800. Okay? So that way I take away the 800 we've already used, and we only pay the additional bit for the stuff that's over 800. And we kind of did that up here when we did 900. We said, oh, 100 was how much we were over when we were 900. Well, how did we find that? We took 900 and we subtracted out the 800, and it left us 100 to multiply with. So this is the same kind of thing here. We've already paid for the 800 by doing this 86.268, so we don't have to pay for it again, so we subtract it out, and we only pay for the excess, a bit above 800. Okay? And so there is our piecewise defined function. Alright, so that is it for section 3.4 about the library of functions. Again, as always, if you have questions, feel free to shoot me an email.